Okay, now we're recording. Okay, so for number 3, for column address 19, 19 decodes to 10011. And each one of those bits is going to correspond to a column address. So the most significant bit is column address 5. Next one's column address 4. This is column address 3, column address 2, and column address 1. So for CA, what was it called? Let's figure out. Oh, it would be really just amazing if I did this now. You guys have no idea what's going on.
No, I understand.
No, I mean.
I understand. I remember I was in your office.
I know.
I didn't want to interrupt you right now. I think I already did.
Okay, we've already messed up the screens enough. I just was turning the screens on. Okay, so LCA 45 is going to be the pre-decode on these first 2 bits. So for 19, those pre-decode bits would be 10, which would correspond to LCA 45 of 2. Okay, I can push the button. Okay. I'm having 2 conversations at once. This is normal life. Yeah, we can do 3. CA2, CA1. There's no CA0 because this was done by hardware people and not programmers. Okay, so the least significant bit, CA3, is going to be 0. CA2 is going to be 1. CA1 is going to be 1. So if I wanted to run that signal to a decoder, because this is 0, to address this row, I would have to do the complement of this. I would have to make this true. It feels like I'm actually doing engineering, and I would have to make this true. So basically, in order to get column address 19 addressed, what I would need is I would need LCA 45 of 2 going to the driver, and I would have to AND that with CA3 not, because I want that to be 0. I'd also have to AND it with CA2 and AND it with CA1. And this would give me column address 19, whatever it's called. So that's what was asking you for in part A. For part B, it's asking you to basically draw the decoder circuits. And the first thing I did for a 2 to 4 decoder, so this is the CA45 circuit. So,
excuse me. So you have to generate that
right.
AND function.
I'm just trying to explain it to you. This is the answer right there. I'm trying to explain to you beyond that what's going on. Make sure everybody understands this.
Oh, okay, thanks.
Okay. Why can't I go to the next page? And try using my mouse. Oh, maybe I have a limit of 100 pages. Okay, a new notebook time. I don't know how to do that. This is my only notebook. So what we will do is we'll go back and scribble on page 99, since there's not really a whole bunch of stuff on there yet. For part B, it's asking you to build a decoder. And you've got 2 input. It's for CA45. So CA45 has 2 inputs, CA4, CA5, and you also have available CA4 not and CA5 not. And you're going to have to build a 2 to 4 decoder. And I asked you to do it with transistors, but I'm going to draw it with AND gates to make it a little bit faster. So for 0, This would be CA, yeah, it's called CA in this case. CA 45 of 0. In order for that to be true, both CA4 not and CA5 not would have to be true. Well, that's an AND gate. Right, right. And you could build the AND gate by building a NAND and an AND with transistors, or you can do what one student did, is do the De Morgan equivalent and invert the inputs. You could do this also. Wait. This is equivalent. Not the inputs. This would be, the second one would be easier to build with transistors. Not the inputs. Remember De Morgan's theorem, A and B is the same thing as double knotted, equals A naught or B naught not. Yeah.
Super useful.
Yeah, De Morgan's comes in all the time. Number 4, let's go back with spaghetti.
So how would you do CA4, 5, 2?
I would just pull in the true lines. I connect these by naming convention, and I would draw 4 transistors, would be the idea. To do the AND gate, I need 6 transistors because I need NAND not. So this would actually become a NAND with an inverter on it, and it would take 6 transistors.
Okay.
Okay, for number 4, you literally go to the diagram in the book and copy it and tell me what the function is for the output for CAM. It is, I'll show you my picture. That might be the easiest way to do it. So it references the diagram in the book. And you go and you find the CAM part of the circuit, which is this string of transistors. It's that thing in the upper left-hand corner. And there's a whole bunch of spaghetti in here. And in order to decipher the spaghetti, what I did is I just put on literally wrote on the gate of each one of those transistors what signal was going there. All those signals would have to be true going in order to get, and then figure out the logic function. If you need more help on that, stop by. I think part of that was actually done in the book. Okay.
Yeah, like the incomplete version was in the
Yeah.
previous page in the book.
Yeah, the incomplete version of that equation was on the previous page of to the diagram of the book. Okay, where are we going to? PowerPoint.
Oh boy, another day.
No. And my mind, my mind's kind of elsewhere, so that was a good break for me. Pre-lecture 9 was due today. Homework 2 is due today. I sent. Oh God, Ben, text me. Oh, you did?
Well, do you mean the email you sent me?
Yeah, no, I know. I got the answer on that. And that's amazing because it's kind of putting the pressure on people because now we have a deadline.
March 3rd.
March 3rd to get some stuff
At
done.
least it's when mine is, but I'm not. I don't have the.
You're like a super senior, so I assume.
The war veterans still get leave before I do.
Okay, but I'm not going to worry about that. This has got to happen fast. For once, the university has to move rapidly.
Oh boy.
I'm scheming. I'm sorry. Text me and tell me to open up the homework till midnight and another submission. If I don't get a text, I will probably not read my email. I'll try to get that open up until midnight if Ben can successfully text me. Okay.
What do you mean text me?
You're texting in class. The teacher's asking you to text in class. Pre-lecture 10 is due on Tuesday. We have some very good news for you guys shortly. And the next homework is due 2 weeks from today. And I will give you a little bit more time on the homework. I don't have a problem with that. I'm just not going to be in my office. I'm going to be giving those poor children a 380 exam. Monday, February 15th at 5:30 in the cave. You can come into the cave. We'll probably go out to, I think I checked, and either 234 or 235 is open. And we can use the projectors on there to project the movie. And we can have a little bit more space, a lot more chairs for people to spread out. We're going to watch Asterix, the Gaul movie. It's called Asterix and the Magic Potion. And if you want to come in through Zoom, the link is the link you're using for class.
It seems better in person as well.
Yeah, we'll have popcorn. We have plenty of popcorn. It'll be in a big bowl. People will have individual plates. And so just scoop it out. And yeah, so we're going to try not to infect the food. You can forego the popcorn if you want to. And so, thank you, Ben. And so, important popcorn information. We'll make it safe. If you're uncomfortable with it, you can bring your own snacks or not eat at all. We're not going to force feed anybody.
Can't have pizza.
We cannot have pizza. We have to stick to flatbread with toppings.
That's our rule.
Oh, really?
They banned pizza for the year.
For just this year?
Well,
Until COVID's over, essentially.
they banned pizza until further notice.
That shouldn't be allowed.
Yeah. Where are we at here?
It's a good thing I brought it.
Good stopping point. Yes, I was suggesting flatbread with toppings.
This is over.
Class is over. Okay, thank goodness. Let's go get some flatbread. Yeah, the other thing is that thing is right in my back. Okay. So the DC sense amp that they're using now is not actually a latch. It's a little bit more complicated because they had to get the sensitivity up. But understanding the place of the sense amp in the circuitry was just an amazing feat for anybody, undergrads coming in and getting hired in that Micron really likes. Or understanding, you know, there could be other circuits where you need a sense amp. We'll get to that later. Okay. So we've got basically what we have here is these are 4 differential amplifiers. And we've got a common current mirror reference here. And we have some output drivers. And we'll talk about the pieces individually. 48 slides. Okay. Now, if enable sense amp is high, so if this is 1, I turn on this transistor, which takes common mode to 0. If common mode is, when it's not common mode, it stands for current mirror in this application. If the current mirror voltage is 0, it goes to the gate of all these current transistors in here. I have 0 volts in there. I've shut off the current supply for all of the diff amps. So the DX, the outputs are going to be floating. You've effectively disabled that sense amp. Now if I enable it, I'm gonna, wow, that's weird. Can you guys see that?
Yep.
Oh, okay. I see a big circle. Never mind. If enable sense amp goes low, then the top transistors turn on, these turn off. This is bootstrapped, which will probably pull it down a little bit and give you a good VREF. It doesn't matter what voltage you have there. All 4 of these current mirror transistors will have the same exact voltage going to it, so they'll have the same current. And then the differential amplifiers will behave like differential amplifiers. So that's one way to disable a diff amp, is turn off its current source. They're all diff amps. And if we look at the gain transistors here, here, these are the gain transistors there and there. They're all NMOS, so this is 4 N-flavor, 4 N-flavor diff amps. They're not directly in parallel because the reason why there's 4 of them. There is one for DX, and DX, you take this IO line, it's driving the IO and the IO star, the output IO and the output IO star. IO star is driving the output DY star and the output DY.
And so what is DX though?
What is DX doing?
No, what is DX?
That is an amazing thing, and I'm looking at that right now. Oh, it doesn't really matter. Okay. Okay. I got it.
I'm just curious because in the previous slide, Dr. Brower was asking us what DX is, and I'm just wondering what it actually is.
Well, DX was floating in the last slide, so we didn't care. But if you look at this, DX star and DY star are tied together. What does that mean? DX star is the inverting version of IO, is tied to the non-inverting version of IO star, and vice versa. So you're just clamping that together a little bit tighter. What do we have here? Oh, we have the first occurrence of the jelly bean. Yeah.
Oh, that.
There's a, yeah. It's another one of Keith's symbols. It's a 1-input multiplexer. It's like a, no, not exactly 1 input. Okay, it is one of these things. See if I can draw it. Transmission gate.
Okay. Makes sense why they would have symbols. It's a little easier to draw.
It's a computer. The computer doesn't care how to draw it.
It doesn't care how much effort it takes to draw it.
You just go copy paste. Boom.
Early designs when people were just like drawing things on napkins.
We didn't have these when people were drawing things on napkins.
We still draw things on napkins.
People couldn't write textbooks when they were drawing things on napkins, is the general consensus from the room. Okay.
Yeah, let's continue.
Okay. Okay. I'm sorry. I had a good day. I just thought. Okay. So this, let's see what this one's doing. This is the driver. The driver is being EQ Sunsant. Oh, stop it. This is what's enabling the drivers. It's enabling these tri-state buffers right here. These are tri-state buffers. I've got pull-ups on those when these signals when the signal's high. When the signal's low, it's going to pull them up, the inputs, and then I've got some more drivers on the output. And we've talked about those drivers recently. There's nobody yelling at me, think. Okay. We've got the timing on the DCSA output waveforms. Again, it's something where I've got to get this in. This is sub-clock cycle timing. This is not something you need to memorize. I just don't. Okay, I'm sorry. Okay. The helper flip-flop. So you've got this array of like 512 sense amps. Divide by 2, 256 sense amps. Each column is going to share a sense amp with the adjacent column in the folded digit line. But they need to fit in a relatively small pitch. So you can't put large transistors in there that are capable of doing a lot of drive. So what they do is along the bus, you know, and because once they take the outputs from the sense amp, those outputs are going to have to drive really long lines back into the data output multiplexer. So there's some really long lines in there. To keep the signal, yeah, I don't blame you. To keep the, I mean,
It was so fast.
to keep the lines from, I'm sorry, I'm just, I almost canceled class today because I'm, yeah, my mind is elsewhere. I can't tell you guys yet. Uh-oh. When are the solutions going to be let's do it. Oh, cancel class today. When are the solutions going to be posted? Probably after midnight tonight, after the due date. Well, we're going to change the due date to midnight. In fact, I could do that right now. That might be a more productive use of my time. Yeah. I have,
That could be the funniest thing I've seen all week.
what?
Having me using them, it's like, I don't blame you.
We're recording this.
Oh, yeah, we are.
Baby learn, and everybody's just going to leave at this point. Sign in. I may.
Just like a cancel class.
Part of this. Okay, recording. I'm just say I'm recording. Don't keep your mouth shut. What am I doing? I'm changing your homework due date. Homework. Homework 2 submission link. So all I have to do is this, edit. You want to talk about to me personally about this when I am not recording, I might say a little bit more. Due date. Oh, I need to make it visible too, don't I? That's different than the due date. I have to do one more thing. I'm sorry, my mind is display after, display until midnight. Because I'm going to be in class until I'll probably be there until like 5:30 tonight. Submission details. As somebody else's multiple attempts, 2 attempts, highest grade. Okay, so I gave you some extra time on that. Okay, so the helper flip-flop, as we were saying, it helps the sense amp maintain the charge on an even longer transmission line than going across the entire column bus. Okay, it's generally pretty small. You can use a latch, back-to-back inverters. You get a full rail from an almost VDD differential input, or as it droops along the line. It's pretty fast. And it's positive feedback because the input feeds into the output of an inverter, which feeds back into the original input. It's just a back-to-back inverter. If you go through all this stuff, what you have here is you have something that's wired up like this. If you take it to the 188 level. And you have these 2 enable transistors here. It's enabled when the clock is low.
Yes.
Because that's all this is. They're using the clock as an enable. Epoch.
Because the M1 transistor.
Yeah. That's kind of weird, isn't it?
The M1 transistor. So if that is high, it would pull it to, it would pull, when this is high, it would pull that node down. When this is high though, it turns that transistor on. No, when this is low, it turns this transistor on. So it's enabled when the clock is low.
Yeah, so it's enabled when the clock's low, pulls to ground when it's high.
Yes. Okay,
Mystery solved.
right. I got into an argument this week. Okay. Someone was trying to convince me that learning how to reduce logic in EE110 was a lost art and nobody uses it anymore.
Yeah.
And it was an FPGA designer. And I went on a long tirade and basically explained to them that you cannot do everything in an FPGA. You can design a microcontroller in an FPGA. They're really powerful. You can do standard, all you're doing in an FPGA is standard CMOS. But when you want to drill down to circuits like these are non-standard circuits. They're a combination, and they're not even, it's not even, we can say they're pass transistor. You can't make these with HDL. They're a combination of standard CMOS, pass transistor, dynamic, analog techniques mixed in there. We've got diff amps in there, and you have another category which I call what the heck it works. And you mix all these together, and this is when you have to fit logic into a small space. You're going to see logic like this if you go to work at Intel, even if you're working on one of their big processors. The processor itself, yes, could be designed in HDL, but all the circuitry that connects the pads to the processors and provides any kind of drive, the power supply circuitry cannot be done in HDL. And it's still logic.
And then you have to do it all by hand and log.
No, sometimes, yeah. Sometimes you have more advanced tools for copying and pasting. Pasta. Don't, Ben, don't distract me now. I'm bad enough right now. It's good news. It's good news for me.
I'm excited.
Okay. So we've got this data read box. We've decided this does not actually read 16 bits out of it at a time. I've gone through this argument yesterday. This only goes 0 to 7. So this is half of the data read mux, but illustrated for the purposes here. Now, if you notice here, depending upon whether I have 16 outputs, 8 outputs, or 4 outputs, I'm going to want to send the signals into different places. Now, if I'm sending out 16 inputs, I'm going to want this signal right here, LV0, going to my 0, 1, 2, ... 7, going all the way down. If I'm only reading 8 outputs, I'm only going to use half of this. So the way I'm going to read 8 out is I'm going to read half the 16-bit data on one cycle and read the other half of the 16-bit data on the other cycle. So I'm going to read 0 on the first cycle and 1 on the second cycle. And here I'm going to read 2 and 3. And then down here on 6 and 7, it goes 4, 5. 4, 5, 6, and 7. So I get half the data out on each cycle. If I go to a times 4, I'm going to have to read 4 out at a time. I'm going to have to make 4 reads of this to get all 16 bits out. The 16 bits are going to be loaded on these lines, or the half of the 16 bits are going to be loaded on these lines, and they'll be read out either all at once in 2 clock cycles or in 4 clock cycles. So here I'm just doing the even bits on the first one, and then I do the odd bits. So it's going to take 4 times as long to read it out. And you can look at the wiring in the book and convince yourself of that. It's just, they're just multiplexers and with enables and inverters and things like that. Okay, the output buffer. I'm going to put the output buffer is going to be a latch. It's going to store data and pipeline that out to the output. So I need a latch to store the data that I want to put on the output, and I'm going to have to store the data in a pipeline architecture so that I can get, sometimes if I'm doing this by 4, it's going to take 4 clock cycles to get all 16 bits out. So I'm going to have to store the previous data and make sure that that gets in there at the right time. For my driver, I'm driving a really big capacitance. Think of most of the capacitance that we're complaining about on the digit line and the column line were like 10, 100 femtofarads. Now we're going up 3 orders of magnitude at about 50 or 100 picofarads. That is the size of a pen on an integrated circuit, probably tied to a PCB trace tied into another IC. So you don't want everything on your chip to be able to drive this. Your output buffer is going to be a really big circuit. You're going to have a lot of power. You're going to have the possibility of disaster when somebody comes along with a scope probe and accidentally shorts 2 pins together. You could potentially short this out. Somebody could not stick the chip in their pocket and carry it across campus. Sorry, Taylor. And do some ESD damage to it. A lot of things can go on with this chip. So we want to look at the output driver. And I'm hoping this is what this is. Yeah, output driver. So basically, I have 2 parts here. I've got a latch to store the data, and that's all this part is. And then I have the driver electronics, and I want to make sure that these are big enough that they can drive that capacitance. Generally, you look at most, my controller, let's put this on the scale. I'd have like a controller that would be like 30,000 gates or something like this. And next to somewhere on the edge here, we'd have a pad. This was where you would do the wire bonding to. And the circuitry around this was visible. I mean, it was like each pad had its own huge drivers on it. Okay. There was a point to actually some of that babbling. The latch, the job of this is to store, and you can, I don't want to go through and analyze things today, my mind's elsewhere. So you can store a 1 or a 0 or tri-state it. We tri-state it with this output enable here. Again, we have the jelly bean symbol. We want it to drive really fast and be able to drive a lot of capacitance. So we're going to have big drivers on this output stage. Well, no, not yet. We're not drive the capacitance yet. But we're going to start scaling the size of the transistors up, because when I have the latch has to, remember the latch has to power the driver. The driver is what's driving the 50 to 100 picofarads. This thing right here, if I made this like minimum size logic, it wouldn't be capable of driving the driver. So you kind of step it up in stages. This is going to be more medium sized. And the original drive circuitry will probably be small drives. And this way, your long bus with the helper flip-flop will be capable of driving something like that. By the time you get out of the latch, you have an output that's stronger, that's capable of driving the driver. So you have to scale things up as you're moving through the output buffer, the output pad. Guess who designed the output pads?
You.
No. Bruce Hancock. Of course. Anything the rest of us didn't want to do. So these are the transistors that are going directly to the DQ pin. These are the ones I need to make really large. Right there. We've got the drive buffer. There's another problem with this. Anything that goes to the pin, remember I told you about the guy with the scope probe coming along?
Yeah, didn't you say that happened one time?
Oh, that happens all the time.
Like you were talking about one time that it happened in particular, like a kid peak, I think.
Okay, I don't remember because
Like any story about
that happened. Yeah, that happened a lot. Some of those drift through my in and out of my head when I'm thinking about them. Okay, here's the problem. The other problem I want to talk about, it's probably on the next slide. If I take, notice every single one of these is NMOS on the output driver. The pull-up is an NMOS transistor. Why did they do that? It was not an accident. We're going to draw a cross section here of a CMOS inverter. I need an N well for the PMOS. I'm going to put P plus diffusions in there. I'm just going to draw them P. And then for the whatchamacallit, and this would be in a P substrate. For the NMOS transistor, I need these N diffusions in here. I have an N, this part's P2. I have an NPNP, or you could call it a PNPN. What have I just built? I built this horrible device whenever you have PN. This is called like a thyristor, I believe is the correct word. It's a cousin of the NPN transistor, but it has this really bad problem. If I accidentally inject small amounts of current into here, it turns on and you can't shut it off.
can't shut off until I assume it just completely runs out.
Until it burns itself out. So shorting these two pins on the IC together might be enough to hit one of these wells with enough pulse of power to turn that pad on and completely obliterate it forever. It's called latch up. We have a name for it. We'll talk about that in a lot more detail when we get to semiconductor physics, but for now I just want to get you the idea. And that's the reason why, if I can avoid putting this N well in here all together on the output, I can avoid the chance of doing latch up. That's why they're all NMOS drivers on here. It wasn't an accident. Means I'm going to have to invert some of my logic to get that thing to
Yeah,
work.
interesting way of getting around that issue.
Yeah. Right. The output drivers have big transistors to drive large capacitance. They generate, they are rapidly switching currents. They're switching both voltages and currents. But remember, the voltage, and those pins are inductive. Anytime you see a wire is inductive. So those wires going to the outside world and going to the PCB trace have inductance. Since I'm switching current, I'm going to get voltage, I'm going to get switching voltage on there also. So this is what's generating some of the little noise blips you see on real signals, is that parasitic inductance. I have a separate external voltage supply. I do not want the crazy PCB designers having any contact with my holy VCC supply that's going all over the chip. I want them to have their separate, have a separate power supply to run those pins. So if the board designer is giving me really noisy signals, those noise signals do not, that I'm getting from the PCB designer, do not propagate into my IC, because I don't want to have to deal with that. And we talked a little bit about latch up, and we'll talk about that in detail and some more of the physics when I have better diagrams. But basically you need this PNP structure. And if you use only NMOS, it eliminates the potential, and we'll explain why in later slides. CMOS would be much faster and easier to drive. Now there's another issue with the output driver is Taylor. Yeah, I'm talking about Taylor Bruce. He walked across campus with 8 MOSFETs in the pocket of his jeans, and Cotton is just like static magnet. Okay, and he gets them up to the lab, and the threshold voltages and then the transistors match. The hit wasn't enough to blow them, but it was enough to do ESD damage. That, and low-level ESD damage raises the threshold voltage of devices. He just put, Sharber handed him to him. Sharber should have stopped him at that moment. Okay. ESD is an acronym for electrostatic discharge. When I want to be, oh God, I shouldn't say that. All my vocabulary's had to change since the 80s. Will you promise not to be offended?
Yeah.
Okay. Okay. When I want to be an ESD Nazi, I'm going to be an ESD Nazi. It's an official. It was an official word. That when I say that, what I mean is, I can be the person, because I've had to do this. I've had to deal with chips that have are very ESD sensitive, that we were not allowed to put protection diodes on. Small sparks can completely destroy electronics. When you go out in the working world, probably within your first week of working, you're going to have to sit through a 4 to 8 hour lecture on ESD. Follow company policy. These are the things they figured out to keep from damaging their parts. I've had to build it up in my own personal lab in Kip Peak. We had a lot of ESD protections, but we added layers onto that. And the guy I was working with at the time and training how to do this is now handling $5 million IRAs for the James Webb's telescope that also don't have ESD protection. So when we were told that we were just blowing the little ASU devices because we didn't know how to handle ESD, if you could have seen the steam coming out of my ears. But the lab up, Cambo's lab, has been completely like, we've got ionizers because the dry air actually produces its own charges, so it neutralizes the air around the devices. We have EOS protection. We have ESD protection. I've gone through the whole thing with a meter looking for static sources. I know there's no static up there.
Yeah, because I remember back in 490 you were saying that like, was it the little like static shock when you like touch door handles? That's
Yeah.
Like 5,000 volts or something?
Yeah, when you touch a door handle and you can feel it, it's in the kilovolt range, if you can feel it. A lot of these devices can be damaged by 50 volts or lower. So it's not just you feeling the ESD zap. There's a lot more low level than that. In most labs, when you're working with equipment, as a test engineer, you're going to be expected to wear an ESD smock. You probably have to wear ESD straps on your shoes, wear these little booties, or go out and buy $100 special pair of shoes that is ESD protective, and get them checked every time you go in the lab. There's a lot of things like that.
I remember sophomore year, Ricardo, I figured out that an RPM only take up to 27 volts.
Okay, you proved that? Yeah. He's saying they did a stress test on an Arduino and proved that it would only take 27 volts of, yeah.
Idea.
Toledo?
Yeah.
Okay. Yeah. There was another Ricardo before him.
And he blew up an LED in my face.
Okay. The Ricardo, sorry. The Ricardo before him was is now a PhD student at Stanford. Yeah. When I ask you to draw the simple voltage pump, this is what I mean. Don't draw the more complicated one. Basically, this clock, and this is the same principles we were looking at before. The clock comes in, and it's going to charge this capacitor. And as it charges the capacitor, and then it discharges. And this charging and discharging of the capacitance is capacitively coupled into the C load. And every time it charges up, it gives you a little bit more charge here. There's no place to bleed off the charge on this one, so it just keeps going up. And this is a voltage pump. We're going to use these voltage pumps, and there's a whole unit on this later, of like a whole set of slides on voltage pumps, so I don't want to spend a lot of time on this now, because we want to be able to generate a couple of voltages. We're going to generate VCCP, which is higher than VCC, so we need a pump circuit. And we need to generate a voltage called VBB. And we'll talk about that one later, why we need that one.
Can we talk about the burn-in range? Because that was one of the things that we lectured that I didn't quite understand.
I'm a little bit behind. We will talk about burn-in. Yes. So we got the whole chip here. Oh, good. I think the last slides go fast. We've talked about the write path and the read path, and you have an idea of everything that's, and there's the memory array. There's a lot more going on in the memory chip than just the memory. You have to be able to address it. You have to be able to get the data to the right location. You got to do the horrible design of the output pin. You've got helper flip-flops along the I/O lines to help you pull that up. You've got an equilibration circuit. You've got the sense amps on the I/O lines, and you've got the data multiplexing. All of this is kind of a cartoon. There's a whole bunch of copies of this as you've kind of learned. For each column, you need a sense amp. For each pair of columns, you need a sense amp. So there is like a whole stack of stuff beyond this. This whole thing is like a big bus. Where am I going here? We've talked about the addresses. A lot of this looks like review to me. The row address and the column address are multiplexed. The bank addresses have their own separate pins to make sure you don't confuse those and you know which bank you're addressing. It always takes higher power to open a row and longer time to open the row than the column. So the typical thing we do is RAS before CAS. Row address strobe goes true before the column address strobe, because you can open one row and then read out that whole column at one time. Right. The columns and the rows are running off of separate circuits, and they run independently of each other. Once I store the column address in from the input pins, I'm going to run that through the column circuitry, and then when I'm reading the row address on the pins, that will be moved into the row circuitry. Hopefully some of this will clear up as we move along. Right, and we looked at the path going through there. They're unidirectional. That means they're not I/O lines. If we go back to that diagram, where is it? Where was I? I was right here, 22. If we go back to the big diagram, there was a way for the column data to get in. There was a separate path for the column data to get out. We want to keep those as separated as we possibly can, if I can't find it. For the row address, it seems jumbled to me. It seems unusually jumbled for Dr. Brower. She usually jumbles a little bit, but not this bad. Coming from the pen, I take the row address, the single bit from the pen, and first thing I want to do is buffer it. And I'm going to pre-decode the upper bits, and I may do this hierarchically. And the advantage of pre-decoding those upper bits is then there's fewer lines I have to send out to the individual row. And I think if you understood problem 3 on the homework, where I'm pre-decoding the first 2 bits, and since I've pre-decoded those first 2 bits, instead of running 2 bits all the way out to the row, I only have to run 1 line for those 2 bits. And I can do that several times and have it so and the logical conclusion is at some point I could actually go to a global row decode where only 1 line is running to each of the individual rows. It still needs a driver because we got to drive the R and C along the line. This is the row address buffer. Row address line, I don't see a lot of, okay, I'm not gonna. Pre-decode circuits, let's talk about these a little bit more. The pre-decode idea, and we've looked at this, is that we've got 2 bits here, row, and which ones is it decoding? I can't read that. This one is pre-decoding bits 1 and 2 because it's called RA12. So I bring in RA1, RA2, RA2 star, RA1 star. I run them into what is effectively an AND gate. NAND, not. And I create for each of the 4 possible combinations of RA2 and RA1, I'm going to create 4 individual outputs. So that's a 2 to 4 decoder. And once I pre-decode those bits, then that is I only have to deal with that one anymore. And this one will go to a quarter of the array. This one will go to a different quarter. And it really makes the routing a lot easier. It's getting harder to explain now that I understand in some ways. This is getting completely random.
Yeah, it feels like that a lot of this is stuff.
A lot of this feels like review, and some of it feels like some new stuff thrown in that we're going to talk more about later.
Like so far there's been about 3 or 4 slides that have been relevant to the pre-lecture for those usually, and then the
Right.
rest of it's been like review from the previous 2.
Okay. Yeah. Dr. Brower was a firm believer in, she went to NAU while she was working and got a French degree, undergraduate degree in French. And what she said was, well, what you did is you kind of learned how the first year you did everything in the present tense. And then the second year you go back and review the stuff you learned in the first year, and then you'd add more stuff onto it. And her theory of education was this is what you needed to do, which is why you learn MOSFETs in 280, and then you immediately go back and review it in 380. And a lot of this is just jumbled review. I'm looking at this, but I didn't have quite enough time. This is what happens when I don't have time to organize my thoughts. Right, if I have 4,000 rows, I'm going to have to refresh them twice as fast than if I have 2,000 rows. Because remember, I have to go back and refresh every row every like so many 40 milliseconds or whatever it is. If I have twice as many, I'm going to have my refresh driver running twice as fast. So that's another thing that limits the number of rows and columns, or the number of rows, I should say. This is a driver circuit. Let me get and the column address path. This is a review of what we've looked at already. If we're looking at, and it's good because I know some of this is new to you, some of this is you need to go back and look at. For the column address, I've got the pen. I'm going to put a big buffer with ESD protection next to it. I'm going to do the pre-decode, and then eventually that's going to go into the master column decoder at every row, and then the column select. If I pre-decode those bits, it's fewer lines I have to drive all the way out to the array. Also in the column, I got to do the equilibration driver, and that will be part of project 2. This is the column address buffer. You got a latch in here. You've got a driver in here. This is not going to the outside world, so I can use PMOS. This driver is a latch also. It looks like it's a tri-stated latch. The equilibration driver, and some of this is just not really all that pertinent. We talked about the pre-decode several times today. Synchronization. I was having, okay. The clock's right here. After the clock edge and you ask for the data out, it takes some amount of time for the data to change. This is when the signal's valid after that clock. If you have higher clock frequencies, the amount of time you have for your data to settle goes down. So all your circuitry has to get higher. Instead of doing that, they went to this concept called DDR, which basically uses a delay lock loop. You're only doubling the data rate on the output driver. You load the data in, you know, like you can load when you can load the data into the output driver faster than you can send it to the outside world. So you can buffer it there and use a delay lock loop to send it out. And I'm going to, the next slide show you that. I did get that far. No, I didn't. Not that one. This is the one I want. This is the idea right here. This is the clock. The clock actually has skew on it. It's not a perfect square wave. It takes time. But when I get that first clock edge, I want to put this data out. And this is DDR2 because it looks like I'm getting 4 data packets out per clock. No signal in there to strobe it. Yes.
Is there advantage to having skew on it, or would it be better if it was a perfect square wave?
If it's a perfect square wave, it's going to have more high frequency components. If you slow it down, you get rid of some of the higher frequency components. The other problem with having perfect square waves is that, think LDI-DT. If DI-DT, if you're switching the voltage, you're switching the current going through that line really fast, you're going to cause larger voltage spikes. So skewing it a little bit gives you smaller spikes on your lines. It helps clean it up. There was something in here I didn't want to talk about. It's a phase detector. Black Magic, PLLs. Basically what they're doing is they're using analog circuitry off the clock edge to generate an analog delay that's a quarter of a clock cycle away let's go back to that slide. I know what I want to say. So for this one here, you're going to have to use an analog circuit called a delay lock loop. They're kind of black magic, and TI sells really good ones. When I need one, I go out and buy one that somebody else has made. But what these things do is, like, maybe let's just say this is a slow clock. We'll call this 100 nanoseconds. If this is 100 nanoseconds, what the delay lock loop is going to do is it's going to produce a pulse that happens 25 nanoseconds after the clock edge to clock in the next bit of data. Another 25 seconds later, it'll clock in the third bit, and then another 25 seconds later, it's going to clock in the fourth bit. Okay. I'm sorry. Okay, you guys are bored, aren't you? And that's what all this is talking about, is delay lock loops. As the input frequency goes up, okay, this thing called jitter, do you guys know what that is?
You've mentioned it before, but,
Right.
but I think it is, but I don't think we can count it about it.
Yeah, I think we're going to do that a little bit more when we get into signal integrity. Jitter is basically a, you have a clock. It's better to do this with a picture. Sometimes the clock goes this, and if you trigger on the clock edge, what you find is you trigger your scope on your clock edge, so it always comes up here, is that next clock edge happens a little bit later. Sometimes it happens a little bit earlier, and there's a whole range of possibilities within there. And that's what engineers call jitter. It's like thermal instability inside the system causing the delays to change. The current is changing a little bit with time, and all these things affect the jitter. This is a good measurement to give to a PUP engineer. Go out and with the circuit and measure what the jitter is, how wide this is versus frequency. And in this case, you can see the jitter is actually larger at the lower frequencies, and I don't quite understand that because I'd expect it to go the other way. Stage delay, this one makes perfect sense. If I go to lower voltage circuits, I get much longer delays than if I have higher voltage circuits. And the delay is a function of temperature too. So a lot of the measurements you're going to be doing as test engineers are going to be like temperature testing, making sure everything still works. What are the delays versus temperature, and making these beautiful Microsoft Excel graphs. And then the whole idea here is how low can we make VCC before our delay gets too high? These numbers are a little bit old, but the same concept's happening now. You could change this to 2 and you could change this to 0.8 and you probably see the same kind of curve. ICC, which is how much current the DLL is consuming versus frequency. Generally, current goes up as frequency goes up. You guys go out, you make the measurement, you draw the pretty graph, and somebody says, okay, this is how much current we can take. We're not running any faster than 200 megahertz, or that number may be 2 gigahertz. So a lot of this stuff, you've just got to test it to death to figure out where you want to operate.
That's again.
Reason why there's so many test engineers in the world. It's a phase detector. I don't want to talk about that. Shift control. Another really popular technique for engineers, gate delays are fairly consistent. And the nice thing is as the temperature goes up and they'll actually get a little bit faster. As the temperature varies in there, the gate delay generated by a double inverter, in that case, that's my double inverter, will give you a consistent delay across there. I've seen people anytime you need to make one signal happen a little bit after another one, they'll put like 12 inverters in series just to make sure and tune the size of those inverters to give you the correct delay using simulation. Transmission gates, I don't want to talk about, oh, that we talked about the tri-state. We got 5 minutes.
Touch on it briefly.
Let's do it good. Okay, sorry about today. I can't tell you guys until I tell Ben. Not you, the other Ben.
Ben Brown.
What?
Ben Brown.
Okay. I'm excited. Okay, so what I've got here is I have a tri-state inverter. Is that right, Dr. Brower? Okay, well, let's try this. It's almost right if it's not completely right. If C is low, that is wrong. What we need here is if we want to enable this with C, let's make C active high. I'm sorry, I've got 5 minutes to do this. If C is active high, and that's our enable, we want this transistor to be on. So that would be C. And we want this transistor to be off. So that is C naught. Now, if C is high, I turn this transistor on and I turn this transistor on. It looks just like a standard inverter there in the middle. In that case, out equals not in. It's a standard inverter. Now let's change this. If we disable it, so not C is high and C is low, then I turn this transistor off and I turn this transistor off. This inverter in the middle is floating. I have no connection to my power supply. This is a tri-state. Okay. It's a slight error, it's not bad. You don't have to build a tri-state. You could, if you wanted to, in your project for your tri-state drivers, use something like this. I think Nigel did that.
Tri-state inverter.
Right. Or you can go to generic 13 and use that tri-state. Be careful. When you use the tri-state in generic 13, it has connections to power supplies that may not have the same name as your power supplies. So you've got to make sure that externally you connect up a power supply to that, whatever that signal name was.
So it might be better to build our own tri-state.
Yeah, some people have had trouble with that tri-state, but it's easier. Yeah, either way, it'll work. And this is the idea. If you want to tap off a clock, what you do is you have an N. You've got a quarter T clock delay. I don't recommend using inverters for this. I recommend using the professionally built DLL. And then people, yeah, I probably. I hate DLLs. It's like controls theory. I'm done.
Oh, maybe the second goes down.
I'm sorry. I will make this up to you on whatever the next day is, Tuesday. I was going. I forgot it. What happened? What actually happened?
Do we want to stop the recording before you tell?
Yeah.
Now it's in the recording.
Okay. It was stop recording so I can talk about